what I'm speaking?
Yeah, it's perfect, I think. So you would prefer to take most of the questions at the end, right? At the end of the talk, or should
I'll leave it to you. If it seems like a relevant or a promising question, you can. I don't anticipate that questions will just come up like that unless they are just clarification questions, because the material is not. It's not like a science talk where you can ask, speculative kind of questions. There will be only something specifically about the problem that I'm discussing. Yeah, if it's fine, I can answer it. There is a board here, so if I have to use a board or something like that.
Great. So if it's a clarification type thing, then if it's a quick clarification, I'll just let you know.
Okay.
So Jasjeet, I'll wait for your signal, or Asha maybe. Let me know when I should get started.
It's already time, I think. Jasjeet might have gone off to have tea.
So should we start?
Maybe we can start. It's time.
Okay, good. Yeah. So welcome back, everyone, to this to the last talk, in fact, of the high school section of this resonance lecture series. It gives me great pleasure to introduce our next speaker, Dr. Shailesh Shirali, whom I've known since I was 11 years old, since I was very small, and I've had the great privilege of studying mathematics with Dr. Shirali when I was in school, so in 11th and 12th standard. So it gives me special pleasure to introduce Dr. Shirali today. Shailesh Shirali is currently the director of Sahyadri School of the Krishnamurti Foundation, India, in Pune. He was earlier principal of Rishi Valley School. He is a trustee of the Krishnamurti Foundation, India, and has been with the KFI schools, that is the Krishnamurti Foundation of India schools, since the 1980s. He has been in the field of maths education for many decades and has helped train the Indian teams that took part in the Indian Mathematics Olympiad, in the International Mathematics Olympiad, I'm sorry. He has a particular interest in ancient Indian mathematics. He has also a deep interest in facilitating inquiry into the fundamental issues among students at the school level. He's the author of many books on mathematics for school students, including Adventures in Problem Solving, a primer on number sequences, First Steps in Number Theory, a primer on logarithms, Adventures in Iteration and Mathematical Miniatures. He serves as chief editor for the magazine At Right Angles, published by the Azim Premji University and Rishi Valley School, together with Sahyadri School of the Krishnamurti Foundation of India. Today, Dr. Shirley is going to talk about problems in number theory arising from high school mathematics. And I'm sure you're in for a great treat today. Sorry, did I say it wrong?
Yeah.
Problems in number theory arising from high school mathematics. And from all my experiences studying mathematics with Dr. Shirley, I'm sure you're in for a wonderful treat today. So over to you, Dr. Shirley.
Thank you very much, Pranav. I'm very happy to be here in this position talking to students on a topic which is very nice to dwell on. If you think of the title that was just read out, Problems in Number Theory that Arise from High School Mathematics. So I'm very grateful to the organizers for giving me this opportunity to talk with all of you. So without further ado, let me share the screen. So good day, all of you. So you can see from the title what this is supposed to be about. And the motto of this talk will be this beautiful this statement that problems are the lifeblood of mathematics. That's the original quote from the great mathematician David Hilbert, who by proposing a number of open problems steered the whole course of mathematics for so many decades. And just to give us an example of how open problems can drive research, just look at this list out here of how, say, the parallel postulate, what's known as the fifth postulate of Euclid, how the whole of non-Euclidean geometry arises from the attempts to prove it, how the attempts to solve the quintic equation have given rise to a very rich branch of algebra associated with Galois. Similarly, Fermat's last theorem, the amazing amount of mathematics that arose from it, and so on, the four-color problem, the prime number theorem. So this open problems are an extremely important component of mathematics. And in school mathematics, it turns out that there are many aspects which allow for the creation of interesting problems. And here by problem, I mean something whose solution is not clear. You have to figure out a way of solving it on your own. So just let me introduce a term which is not really a part of mathematics, the notion of a nice problem. So a nice problem is one in which the input data and the answer are both rational numbers. And not nice problems are presumably those for which the input data or the answer feature irrational numbers. And as you can guess, mathematics teachers love nice problems, and for the very simple reason that nice problems allow students to concentrate on important ideas rather than get caught up in messy calculations. And the person who introduced this notion of a nice problem made a tongue-in-cheek conjecture. He says, a great deal of classical mathematics was invented by maths teachers who wanted to make up nice problems. So I find that quite witty. So he, in fact, calls the act of creating a nice problem, the mathematics of it, a meta problem. So what we are going to be discussing today is something of that kind. So the most famous meta problem, of course, is finding Pythagorean triples. That is, triples of integers that can be the sides of a right triangle. For example, 5, 12, 13. And if you actually make a triangle with sides 5, 12, 13, you can see that the sine of this angle t is 5 upon 13 and cos is 12 upon 13, which means that both sine and cos are rational numbers. So basically you can say that this problem automatically arises when we seek angles for which both the sine and the cosine are rational numbers. So even if you never knew about Pythagoras or Pythagorean triples, any trigonometry, the teacher who is teaching trigonometry will be confronted with this problem because he doesn't want to have problems with roots and all that. Now, before I go on, I just want to mention this, that there is a very well-known scheme for generating Pythagorean triples. And I've written out here, assumed to be well-known. And the scheme is simply this: choose any two positive integers m and n, with m more than n. compute these three numbers, A, B, and C, defined by A is equal to B squared minus, M squared minus N squared, B equals 2mn, C equals M squared plus N squared, and then this is satisfied. So you can get this Pythagorean triple ABC from this. And if you want to specify more conditions like the numbers should be co-prime, well, you just have to put some conditions on M and N, which we need not bother about right now. And the important thing is, I'm not going to derive this formula right now, but some of the problems that are going to be studied today, if you actually follow that method, you can derive this on your own. So I'm addressing this to the school students here. So let me look at the very first problem of this kind. Now in the Pythagorean triple problem, basically you're looking at triangles which have a 90-degree angle, right? They are right triangles. Now you can change this angle and look at other triangles. So instead, let's focus on triangles with a 60-degree angle. How would one generate triples of co-prime positive integers, which are the sides of a triangle with a 60-degree angle? So that's the problem. So it's exactly like the Pythagorean triple problem, except that you have substituted 90 with 60. So first of all, so how I'm going to derive it like this. Let ABC be the sides of the triangle, and angle C is assumed to be 60 degrees. So by applying the cosine rule, since cos of 60 is half, you get C squared equals A squared plus B squared minus AB. So the task now is solve this equation. That means find integers A, B, C satisfying this equation. This symbol here is the symbol for positive integers, a set of natural numbers. Now I'm going to convert this problem slightly, move out of the integer set of integers by dividing throughout by C squared. So after dividing by C squared, you've got an A upon C whole squared and a B upon C whole squared. So I write X equals A by C and Y equals B by C. And then the equation becomes X squared minus XY plus Y squared equals 1. And now instead of looking for positive integers, well, this problem has now got transformed slightly. You're looking for positive rational numbers satisfying this equation. So we have to figure out some way of getting these rational pairs. Now, I'm going to show you a very nice method for doing this. And it turns out that exactly the same method will work for the Pythagorean triple problem. There you'll see that just this xy term is missing. You've got x squared plus y squared equal to 1. And exactly the same method is going to work there. So first of all, let's look at this equation, x squared minus xy plus y squared equal to 1. If you plot it in the xy plane, you will find that it represents an ellipse. And you can see from the symmetry of the equation that it's going to be symmetric in the xy axis. The xy equals x is in fact an axis of symmetry. And what are we interested in? We are interested in the rational points on this ellipse. That is, the points with rational coordinates. Rational points means points with rational coordinates. We are, of course, interested only those in the first quadrant. And we are going to make use of one particular rational point on it, which is P minus 1 minus 1. You can check that this satisfies this equation here. Just substitute and you'll find it. In fact, since P minus 1 lies there, so does Q11, which I have marked it out here. I have not put it, well, it's not Q, sorry. It's the mirror image of P. So I'm going to write Q for any point of this kind, a rational point in the first quadrant. Let L be the line passing through P and Q. Let T be the slope of this line. Then obviously T is a rational number because Q has rational coordinates and this is also rational. So it's obviously the slope is a rational number. So what it boils down to is you've got two equations. First, you have the equation of the ellipse x squared minus xy plus y squared equals 1. And the equation of the line is obviously, I'll go back here, since this point is minus 1 comma minus 1 and the slope is t. So the equation becomes y plus 1 equals t times x plus 1. And from here, if you substitute for y into this equation, you get this quadratic equation. I've left out the steps. You can check them out for yourself. You get this quadratic equation in which the coefficients are expressions in t. Now, obviously, one root of this equation is going to be minus 1. Why naturally? Why? Obviously, because it passes through the point P. It passes through this point, this line. So this is one point of intersection of the line and the ellipse. So naturally, -1 is a root. And now you can use the fact that the sum of the roots of a quadratic equation is minus of this coefficient upon this, or even simpler, the product of the roots is equal to this part, the C part upon the A part, right? The constant term upon the coefficient of x squared. So you can easily get the second root without any calculations. It turns out to be this, minus of this quantity upon this quantity. And this naturally corresponds to Q. So if you work out the y coordinate based on this, you get this expression. So now notice that if you put t equal to any rational number, this will be a rational point because all rational operations out here. And since you want this to be in the first quadrant, this should be positive and this should be positive. So you get a certain interval for t, and that interval turns out to be half to 2. T corresponding to rational numbers and half less than t less than 2. And that's it. All you have to do is take various values of t in this interval, substitute in here and calculate it. For example, take t equal to 2 by 3. It satisfies this. You plug it into that formula, you get the 0.8 upon 7 and 3 upon 7. And that gives you the side of the triangle, 8, 3, 7. Because remember, all we do is clear the denominator. So you get the ABC as 8, 3, 7. Take t equal to 3 by 4. You get 15, 8, 13, and so on. And so you see this very simple method of drawing a line with a rational slope and intersecting it with the curve. And that's it. Like as though by magic, you've managed to get all the points. You might wonder, do I really get all such triangles? I'm going to leave that question for you to answer. Or by some chance, are some triangles missed out? For example, do you get the equilateral triangle from this? Equilateral triangle obviously is a triangle with a 60-degree angle. Can it be obtained by some value of t? Yes, it can. But I'm going to leave this question for you. Does it satisfy? Do we get all such triangles? And also, by some chance, can it happen that you get a triple ABC for which the triangle inequality is not satisfied? I'm going to leave that also for you to answer. It's a nice problem to settle. Okay, so just in passing, before we move on to another kind of problem, I'm going to ask, does there exist a lattice point equilateral triangle? And what is a lattice point triangle? A triangle in the coordinate plane in which all three vertices have integer coordinates. So those points are called lattice points. It comes from the word lattice, which has other associations with crystals and so on. So lattice point, you can get this equilateral triangle. So does there exist a lattice point triangle which also happens to be equilateral? Well, you can, though we just settled the question of a triangle with a 60-degree angle, this turns out to have a different solution. So the answer is no. Not only does there not exist such an equilateral triangle, it is not even possible to find a lattice point triangle with a 60-degree angle. So here's the proof. So this is an example of a negative result. So on the left side, I've shown a possible lattice triangle. Now, for any such triangle, you can see that this conclusion must hold. Take any of the angles, let's say angle A. Either it must be a right angle or the tangent of that angle must be a rational number. There are no other possibilities. Why should it be a rational number? Well, if these are lattice points, then obviously the slope of AB is rational. The slope of AC also is rational. And now by simply substituting into that well-known formula, tangent of the angle between two lines, which is studied in coordinate geometry, you'll find tan of the angle is a ratio of two rational numbers, therefore it's rational. But tan of 60 degrees is √3, which is an irrational number. So conclusion, A is not equal to 60 degrees. So you can't make a lattice point triangle with a 60-degree angle. And immediately the question you might ask, how close can we get to an equilateral triangle? Now that's a nice question. Obviously, since you can't get an equilateral triangle, you might want to see how close you can get. Maybe two sides equal and the third almost equal to these two? Well, I leave that question to you. That's it takes us into a different territory. So the next question I'm going to ask is connected with the topic of sequences, right? You study in the 11th standard or maybe even earlier 10th standard, this arithmetic progressions, geometric progressions, harmonic progressions. And you might want to ask, how do we find all instances of three perfect squares in arithmetic progression? Now, it's not easy to actually think of three such squares, but after thinking for a little while, you may come up with something like 1 and 25 and 49. That is 1 squared, 5 squared, 7 squared. That's three perfect squares in arithmetic progression. So we can ask, how do we get more such instances or maybe all such instances? And what about the case of 4 squares in arithmetic progression? So I'm going to answer the first question here and just say a couple of lines about the second question. So let's see. So let the squares be called a squared, b squared, c squared, and we are assuming here that they are not the same, they are distinct. So 0 less than a less than b less than c. So by the definition of arithmetic progression, b squared minus a squared equals c squared minus b squared, which means 2b squared adds up to a squared plus c squared. And I'm going to do something similar to last time. Divide throughout by b squared. So on the right side, you get a by b whole squared and c by b whole squared. So write x and y for these numbers. X is a upon b, y is c upon b. Then like last time, x and y are positive rational numbers. This, by the way, is the symbol for rational number. So x and y are positive rational numbers, and the sum of their squares is 2. So just like last time, you have this problem. Find all x and y satisfying this equation. Now I'm going to show you two ways of proceeding. One is exactly the same as last time. So I'll just have a single slide on it, graphical, and then, or I'm going to show you an interesting low-tech way of solving this. It is low-tech because it's literally low-tech. You just see in a minute. So what's the graphical way? Well, we plot the equation x squared plus y squared equals 2. It's a circle with center 0, 0 and radius root 2. And our interest is rational points on this, which lie on the first quadrant. And it happens to have one particular point of interest, which is p, just like last time, -1, -1. And we're going to use the same idea. If q is any rational point here and you join p to q, you'll get a line with rational slope. And the two equations are respectively x squared plus y squared equals 2. That's the equation of the circle. And the same like last time, this is the equation of the line. And you can solve these simultaneously and proceed in exactly the same manner. But you might complain that that would be a bit boring because we've already done one problem of that kind. So I'm going to proceed in a very different way. Okay, I'm not going to continue this particular analysis. So I'm going to show you a low-tech solution. So what's the low-tech solution? So I'm going to rewrite x squared plus y squared equals 2 as x squared minus 1 equals 1 minus y squared. Then you factorize x squared minus 1 as x minus 1 times x plus 1. Factorize this in the same way. And then by division, you get an equation like this. X minus 1 divided by 1 minus y equals 1 plus y divided by x plus 1. And since they're equal and they are both rational numbers, remember that x and y are rational numbers. So this quotient is a rational number. It's a positive rational number. So put that rational number equal to t. It's some positive rational. So you rewrite then. You get x minus 1 equals t times 1 minus y. And 1 plus y equals t times x plus 1. And you can treat these now as a pair of simultaneous equations, linear simultaneous equations in x and y. And it's very easy to solve them. Again, I'm not going to go through the solution. You solve them and you end up getting this answer. X equal to this ratio of two quadratic expressions. Similarly, y is the ratio of two quadratic expressions. And that's it. We've got the answer in terms of a rational number t, positive rational number. Now it's just a matter of substitution. Of course, we also want the numbers to be positive, which means we want the denominator is always positive, t squared plus 1. So you want the numerators to be positive, which means 1 plus 2t more than t squared and t squared plus 2t more than 1. Well, if you solve that, you will end up getting this interval. I'll leave out the details again. T must lie between root 2 minus 1 and root 2 plus 1. And now just take any t and substitute it into that. For example, take t equal to 3 upon 2. Just put t equal to 3 upon 2 here and just plug through the calculations, and you will end up getting 7 upon 13 and 17 upon 13 for x and y. So you get the three perfect squares as 7 squared, 13 squared, and 17 squared. And you can check that you've really got three squares in AP. 49, 169, 289, and similarly you get all these others. So you can get, in fact, as many as you want. Any value, any positive value of t, rational value of t between these two will supply you with a solution. So it's interesting that something which doesn't look obvious has got such a simple answer through the solution of equations. And now, just to say something about the four squares in arithmetic progression, it's very surprising, considering that it was so easy to find three squares in arithmetic progression, and there are infinitely many such instances. It is not possible to find four distinct perfect squares in arithmetic progression. Well, they don't exist. But the proof is not easy. In fact, it's quite a challenge to reconstruct this proof. As usual, it was first announced by the great Fermat, and as usual, he never proved it. He claimed it in a letter, and there was no evidence that he ever had a proof. So nothing more can be said about it, except that this is a very interesting problem, to find new proofs for this claim that there are no four distinct perfect squares in AP. And this question I won't say anything more about. What about three squares in harmonic progression? Maybe I'll leave it for you to tackle. Three squares in geometric progression is trivial, so there's nothing much to say about that. But harmonic progression is an interesting thing. So let's move on. Here's another interesting problem which ought to come up in school trigonometry, but does not, which is isosceles triangles are, of course, very familiar objects. But what about triangles in which one angle is exactly twice another? Turns out to be not so. You've hardly ever seen seen any result about triangles, proceeding from this. So the question now arises, is there a nice way of finding integer-sided triangles in which one angle is exactly twice another? How would we do this? So here's a nice theorem, which I'm going to state. And some of you may want to investigate this theorem yourselves. It's a characterization of triangles in which one angle A is double of angle B. So if you look at triangle ABC, this angle has been called 2 theta, this angle has been called theta. And it turns out that if angle A is twice of angle B, then you have this very nice relationship between A, B, and C. A squared equals B times B plus C. And what is more, the reverse also holds. If A squared is equal to B times B plus C, then angle A is twice of angle B. So it's an if and only if condition. In other words, it's a complete characterization of such triangles. So before one rather trivial, apparently trivial observation, which is useful, is that this relationship is homogeneous. All the terms are of degree 2. A squared is of degree 2, B squared is of degree 2, BC is of degree 2. And that is natural because a triangle is scalable, right? If you scale the triangle, that is just magnified or contracted, all the sides go up in the same ratio and the angles are unaltered. So this relationship is obviously going to, if it is true at the start, it will remain true afterwards also. So it is natural that this will hold. So we are looking for integer solutions to this equation. with ABC co-prime. That means they must share no common factor. So before we do that, let me just show you a simple proof of the characterization. It's a proof based on trigonometry, and I'm going to leave it open to you to find a proof using pure geometry. It's very nice to look for a proof using pure geometry. Just as a in-between comment, let me say that often, geometry is studied very intensively in classes 9 and 10, or not very intensively, somewhat intensively. And we completely leave pure geometry once we get into 11th standard. Instead, we have coordinate geometry, which is very algebraic, and trigonometry, which is also very algebraic, symbolic. So you lose contact with this pure geometric reasoning. And whenever we meet a geometric statement, our immediate tendency is to prove it using algebra, using coordinate geometry or trigonometry. So it's a pity that I myself have given a proof using trigonometry here. But it's a very nice challenge to try to take up. Find a pure geometry proof of this very same statement. Anyway, here's the trigonometric proof. So I call this theta, this is 2 theta, then this angle is 180 minus 3 theta. So let's apply the sine rule. So you get A by sine 2 theta equals B by sine theta equals C by sine of 180 minus 3 theta, which is sine of 3 theta. And now just multiply through by sine theta. So here you will end up getting A by cos 2 cos theta equals B. And if you simplify sine 3 theta upon sine theta, you end up getting this expression here, 4 cos squared theta minus 1. And that gives you this. From this relationship, you get 2 cos theta equals A upon B. And from here, you get 4 cos squared theta minus 1 equals C upon B, which means that you have C upon B equal to A squared upon B squared minus 1. And if you simplify that, you end up getting that expression A squared equals B times B plus C. And I'm going to leave it to you to show the opposite is also true. And let me now give you a nice challenge. Find a pure geometric way of proving this, not just a trigonometric or coordinate geometry way. Find a geometric way of proving that if A squared equals B times B plus C, then this is true. Anyway, I'll leave that proof now. Now the question is, we have to find positive integers A, B, C in such a way that A squared equals B times B plus C. And this turns out to be simplicity itself. What we'll do is solve it not over the natural numbers, but we'll solve it over the rational numbers. And then we just scale up. We scale up to remove all the denominators. And it works. So the y should be obvious. So what do? Put b equal to 1. So then and put a equal to t, which is a parameter. So you get t squared equals 1 times 1 plus c. That means t squared equals 1 plus c. So c equals t squared minus 1. So ABC is t, 1, t squared minus 1. And you've got your triangle right away. But it must be a real triangle, which means the triangle inequality must be satisfied. So what must be true? All the terms must be positive. T must be positive. T squared minus 1 must be positive. And also the sum of any two sides must be more than the third. So t plus 1 should be more than t squared minus 1. T squared minus 1 plus 1 should be more than t, and so on. So you get 3 such inequalities and 2 more here. If you solve them all together, which is a routine task, you end up getting that t should lie exactly between 1 and 2 without hitting either of these two endpoints. And once that's it. So let t, now remember the formula that we had. It was the triple was t, 1, t squared minus 1. So we put t equal to m by n, where m and n are positive co-prime integers. And then, so it is m upon n, 1, m squared upon n squared minus 1. And if you remove the denominators, you get this. mn, n squared, m squared minus n squared. So we've got it. We have managed to get a triple of co-prime integers for which one angle is exactly double of another angle. So you can generate as many of them as you want. So you get all triples. I've claimed out here all, nothing is missed out. All triples of co-prime integers for which a squared equals b times b plus c. And keeping in mind those two boundaries, it should not be less than 1 or more than 2. So you can look at these 3 by 2, 4 by 3. For 3 by 2, you get a nice combination, 6, 4, 5. M and N could turn out, well, you just substitute it. Well, 3 by 2 means M and N are 3 and 2. So Mn is 6, N squared is 4, and this is 5. And you get this here. And you get a nice result here, which would not have been obvious at the start. If co-prime integers A, B, C are the sides of a triangle in which one angle is A is double of B, then both B and B plus C are perfect squares. Why? B is N squared and B plus C means this plus this, which is M squared. So you'll notice that the formula itself is leading us to this result. We may not have, if we just generated a few numerical examples, we may not have noticed the pattern, but the formula itself gives it to us. Yeah, so incidentally, this particular example, please note 6, 4, 5, which can be written as 4, 5, 6. So that's a very special triangle. It's a triangle in which the sides are consecutive integers, 4, 5, 6. And it turns out that it is the only such triangle. That means it is the only triangle in which the sides are 3 consecutive integers and one angle is double of another angle. That particular problem, by the way, was posed as a problem in one of the International Maths Olympiads long back, way back, maybe in the 1970s or so. Prove that there is just one such triangle, and it turns out to be this. So this triangle, you can say, is doubly special. Incidentally, I should say that the standard of problems in the International Maths Olympiad has changed enormously over the decades. The problems asked in the 1970s were of this kind, fairly accessible. These days, they are much more specialized and rather more challenging. Okay, let me ask this question. Integer-sided lattice triangles. So we are familiar with integer-sided triangles. I've just been talking a lot about them. We looked at Pythagorean right-angled triangles with integer sides, 60-degree triangles with integer sides, and then triangles with one angle double another. And I also mentioned lattice triangles. Can we find a supply of triangles that have both these features? Now, who would want to answer this question? Well, probably any maths teacher who is teaching, who is first teaching coordinate geometry and is teaching the Pythagorean formula. So he or she would want to give examples where the answers are going to come out to be nice integers, nice whole numbers. Remember the definition of nice, which was given right at the beginning. But how do you generate such triangles which have both these features? Now I'm going to show you a unique method which is quite different from what we've done till now. Basically, I'm going to, so just to restate the diagram, the question, how do you generate lattice triangle OAB whose sides OA and OB and AB have integer lengths? And without loss, I can assume that one of the vertices lies at the origin of the coordinate system. Obviously, I can simply translate a triangle and bring any vertex to any other vertex, and the property will remain the same. So I'm going to assume that one vertex lies at the origin. So I'm going to solve this problem using unexpectedly complex numbers. And I'd like to just mention here that complex numbers are actually a very rich field. There's a rich connection between number theory and complex numbers. Many results in number theory assume a different form when you bring in complex numbers into the whole discussion. It's very unexpected, but once they enter the picture, they transform the whole subject. So here is the situation. We embed the triangle in the complex plane. Here's the real axis, the imaginary axis. let A and B be the affixes of these 2 points, which means the complex numbers corresponding to these 2 points. So what is, if you state this algebraically, what do we have? Look at the symbol here. I'll just introduce this symbol, Z with this square bracket I. So this set of all numbers of the form m plus ni, where m and n are integers, if you take this entire collection, all possible such numbers, they are referred to as the Gaussian integers, after Carl Gauss, who was probably one of the first to really study them in this sense, to actually study them as objects of interest in number theory. So find a pair of Gaussian integers such that a and b and a minus b are integers. So what is this cardinality of A is the length of A, cardinality of B is this length here. And sorry, this doesn't mean that it has to lie along the real axis, by the way. This is just, it could be anywhere. And A minus B is the length of this side here. So you must select two complex numbers such that all these three turn out to be integers. Now, I'm going to make an important point out here. Rather than solve this in the most general way possible, I'm only going to look for a way to generate infinitely many solutions. And I'm added out there, it makes sense. Why does it make sense? Well, sometimes to solve a problem in the most general way possible may either be impractical or too difficult, or you may not just have the idea. And I'll give you a very well-known example of this before moving on. Suppose I look at the problem of wanting to prove that the number of primes is infinite. And think of what Euclid did. The original Euclidean proof, you say, let there be n primes, the first n primes, and can I show that there exists another prime apart from these n? Which means any set of primes can always be enlarged by one more. And then you can just continue that forever. So that shows that the number of primes is infinite. Now, a natural problem may be that if you have the first n primes, exactly in sequence, the first n primes without anything missed, find a formula for the next prime, the n plus 1th prime. Now, this turns out to be an extremely difficult problem. And probably it may be still unsolved. And Euclid, very interestingly, did not ask this problem. He asked something much simpler. He says, given these n primes, can I produce one more? So he did exactly what was required. He simply found a way of generating infinitely many prime numbers rather than say, I'm going to generate all the prime numbers, which is too difficult a problem. So I'm going to do something similar here for this problem. So now, supposing we choose A and B, the two complex numbers, so that they themselves are squares of Gaussian integers. That is, A is some alpha squared, B is some beta squared, where alpha and beta both are in this set, and in such a way that alpha squared minus beta squared is itself a square. That means alpha squared minus beta squared is some gamma squared for some other gamma also in that set. Then it will happen that A and B and A minus B will all be integers. Why? Because the cardinality of alpha will be the square root of some integer. So when you square it, you'll get an integer. Similarly for B, similarly for this. So you'll get all three are integers. So the question therefore boils down to solving this equation here. And that means the problem boils down to finding Pythagorean triples, not in the set of integers, but in this peculiar universe, this universe of Gaussian integers. And here a most remarkable situation arises. Just let me remind you of the formula for finding Pythagorean triples in the set of integers. So I'm going to use the same symbol, alpha squared equals beta squared plus gamma squared, but over Z, that is the set of integers. Choose any two integers C and D in Z. Write beta is equal to C squared minus D squared, gamma is equal to 2CD, and alpha is equal to C squared plus D squared. And then it turns out that this is satisfied. For example, if you choose C is 8 and D is 5, then beta will be 64 minus 25, which is 39. Gamma will be 80 and alpha will be 89, and you can check that this is true. Now, the miraculous thing is that exactly the same generating formula can be used in this whole universe. The same method works for solutions in this set. So you pick any two Gaussian integers C and D, and let alpha be C squared plus D squared, beta be C squared minus D squared. So remember that alpha is this side and beta is this side. So alpha is C squared plus D squared, beta is C squared minus D squared, and that's what we are doing. So pick any two C and D and do this, and then the triangle with vertices 0, alpha squared, beta squared will have the desired property. And that's it, as simple as that. So just to give you an example, just randomly select two Gaussian integers, 2 plus I and 1 minus I. If you compute this squared plus this squared, you will find it gives you 3 plus 2i, and 2 plus I squared minus 1 minus I squared gives you 3 plus 6i. And then you square 3 plus 2i gives you this, 5 plus 12i. Square 3 plus 6i gives you this. And we have our triangle. From 5 plus 12i, you get 5, 12. From minus 27 plus 36i, you get minus 27, 36. And so the triangle with vertices 0, 0 and 5, 12 and minus 27, 36 will have integer sides. And you can easily check that the sides come out to be, well, 13, 40 and 45, all three integers. And just one more such example. Take C is 4 plus I and D is 1 plus I. Just run through these calculations and you will find you get another lattice triangle, and it has integer sides here. So it's very beautiful that the same generating formula which works in the set of integers also works in the set of Gaussian integers. Now, there is a reason for this. I shouldn't give you the idea that it is just some magic which is unexplained. It's very simple to explain why, but I have not gone into that. And also, just like there is a low-tech way of getting solutions to the Pythagorean equation, there's also a low-tech way which will work here. Again, I am going to leave that to you. So let me just see now. I have one or two more problems which I'll share with you. Here's an interesting problem. Again, a problem which arises from geometry. Now, I'm sure you know this, these formulas, that if you have a triangle with semi-perimeter S and the radius of its incircle is R, then its area is R times S. All of you must be knowing this formula. So if you take the triangle with sides 3, 4, 5, the Pythagorean triangle, its area is half of 3 times 4, which is 6. And its semi-perimeter is also 6, which means its in radius is exactly 1. And here, so an interesting question arises. So the 3, 4, 5 triangle has got in radius 1. Can we find other integer-sided triangles whose in circles have radius 1? So let's look at this problem. I'll just ask a question. Pranav, how am I doing in terms of time?
So I think we have until 5:30 and it's 5 now. So about 30 minutes more.
Oh, we have time then. I'll go on for about 15 minutes more and we leave it open for any questions after that. So to start with, I'm only going to look at right angle triangles like 3, 4, 5, and then I'll extend it to all triangles. So let's look at the right triangle situation. I'm going to call the sides ABC, where the hypotenuse is C. So C is the right angle. The semi-perimeter is A plus B plus C by 2. And I won't derive all these relationships, but you can easily work them out. They're all standard things they're there in your trigonometry books. This segment is S minus A, there's also S minus A, etc. The in radius turns out to be equal to S minus C for such a triangle. And since S is this, S minus C simplifies to half of A plus B minus C. And you're told that the in radius is equal to 1. which means basically a plus b minus c is equal to 2. So you're looking for a right triangle ABC in which you have this relationship a plus b minus c has to come out to be equal to 2. So this is the task. Find ABC in the set of integers such that positive integers such that a squared plus b squared equals c squared and a plus b minus c equals 2. So if you just substitute for c, you get that, and you open it out, you get this here. And you can bring everything to this side and you end up getting this equation here. ab minus 2a minus 2, 2b plus 2 equals 0. This expression, if you look at it carefully, you'll find you cannot factorize it. But a simple tweak allows you to use factorization. If this number, instead of being 2, if it were 4, that would allow you to factorize it. So, but that itself allows you to solve the equation. So you just add 2 to both sides, and then this factorizes as a minus 2 times b minus 2 equal to 2, which means that you have written 2 as a product of 2 positive integers. Remember that a and b are positive integers. So, and the only way of writing 2 as a product of 2 positive integers is 1 times 2. There's no other way. Which means that a minus 2, b minus 2 are the same as 1 and 2 in some order. That means a and b must be 3 and 4 in some order, and therefore c is 5. So that's an interesting thing. We started by saying that the 3, 4, 5 triangle has got in radius 5, and now we've got this interesting conclusion. That is, it is the only integer-sided right triangle which has in radius 1. Now let's take this, extend this. What about triangles that are not right-angled? So this, of course, is a little bit more challenging. So we have the sides of the triangle ABC, semi-perimeter this, area of triangle, that's the well-known Heron's formula. And also you have this formula, radius of incircle is the area upon the semi-perimeter. So if that means if you're saying that the in radius is 1, that means s times s at this quantity whole divided by s has to be equal to 1. If you simplify that, take away the square root sign, it turns out to be this: s minus a times s minus b times s minus c equal to s. And now introduce some new symbols, x, y, z for these, right? X, y, z for s minus a, s minus b, s minus c. Then the sum of x, y, and z is 3s minus 2s, which is s. So basically, the product of these 3 is equal to their sum. So you need 3 numbers whose sum equals the product. And they are positive numbers because s minus a has to be positive. That's the same as the triangle inequality. Now, if a and b and c are integers, it is possible that s is not an integer. S could have the denominator 2 in it, because you're dividing by 2 at one stage, which means that x, y, z also may have denominators 2. So we have to, that means that we have to settle that question before we proceed. Do we want solutions only in integers, or do we allow denominator of 2? Now, note that this equation is not homogeneous. So some of the things that we tried earlier are not going to work. Now, since ABC are integers, the semi-perimeter is either an integer or a half integer, which means that x, y, z, if it is an integer, then x, y, z are all integers, right? Because it's difference of 2 integers. And if it's a half integer, then x, y, z are all half integers. That means all of them will have denominator 2, right? S minus a is something with a denominator of 2 minus an integer, so it'll have a denominator of 2. But if they are all half integers, then x, y, z is going to have a denominator of 8, whereas x plus y plus z would have a denominator of 2. So this equation will not hold. So it was useful to us that if any of them is a half integer, actually all of them turn out to be half integers. It's not only one of them. So that means that k's can be ruled out altogether, and all of them are positive integers. So basically you have to solve this equation only over the positive integers. X, y, z equals x plus y plus z. Okay. Now, so I'll show you an interesting technique for solving such equations. You should look at the bounds on all the variables involved. These are useful problem-solving techniques, just like that factorization trick that I showed in the previous case, where we added a term to the expression and made it factorizable, and then use the factorization of integers to solve it. So similarly, there's a simple idea here of looking at the greatest possible value of the variables. So as the equation is symmetric in x, y, z, there is no loss in supposing that maybe x is the largest of the three. X is greater than or equal to y or z. So that means that x plus y plus z is less than or equal to 3x, because x is the largest. And x plus y plus z is given equal to x, y, z, which means that you have x, y, z less than or equal to 3x. Cancelling x, you get yz less than or equal to 3. And that's very convenient for us, because now the product of two positive integers less than or equal to 3, there are very few possibilities. Either they are both 1, or one of them is 1 and the other 2, or one of them is 1 and the other is 3. That's all. There are just 3 possibilities. If they're both 1, then the equation x plus y plus z equal to x, y, z becomes an impossible equation, x plus 2 equal to x. So that doesn't have any solutions. If one of them is 1 and the other is 2, then x plus y plus z becomes x plus 3. X plus 3, and that becomes equal to 2x. So you get x equal to 3, and therefore, and you've got already yz equal to 1 and 2. So you get x, y, z equal to 3, 2, 1. And the third possibility, if you just try it out, gives you exactly the same. That means that this equation, x plus y plus z equal to x, y, z over the positive integers, has just one solution. That means 1, 2, and 3 in some permutation. And once you have them equal to 1, 2, 3, you can get all the others. So s is equal to x plus y plus z, which means it is 6. And therefore, ABC is equal to 6 minus 3, 6 minus 2, 6 minus 1, which means 3, 4, 5. Which means you've got exactly the same triangle as earlier, which is really quite surprising. That means that 3, 4, 5 triangle is really unique. There's only one integer-sided triangle which has in radius 1. Not only it's among right angle triangles, it's among all triangles. So it's quite a happy triangle. It is special in so many ways, consecutive integers, etc. In fact, if you actually play around with problem solving, you'll find 3, 4, 5 is one of those miraculous triangles which keeps on occurring in numerous configurations. I wonder how many of you have tried this problem in origami. If you take a square sheet of paper, in origami, all you're allowed to do is various kinds of folds. And by simply folding a paper in like this half, you can bisect a side. Half is very easy because you simply fold something onto itself, you get bisection. But how do you trisect a side? Is it possible to achieve trisection using folds? And remember, the rules of origami are no estimation is allowed. It has to be exact. Well, it turns out that there is a nice method, and that method, again, inside it, you find a 3, 4, 5 triangle appearing beautifully. It's one of those amazing triangles which keeps coming up everywhere. So I have exactly one more problem to show you again, and it has a nice connection with a previous problem. Just like you have nice problems in general, I'm going to look at the notion of a nice quadratic. So quadratics can be nice, of course, in various ways. They can have integer roots and etc. So here I'm going to use it in a very specific sense. If you have a pair of quadratics x squared plus ax plus b and x squared plus ax minus b, so you have two different quadratics here. and you want their roots to be, all of them to be integers. So you get 4 distinct integers, which are the roots of these 2 quadratics. Can we find all such pairs A and B? So how would we do this? So, well, let A and AB be integers in such a way that these roots are 4 distinct integers. Now I claim that for this to happen, the following conditions are necessary as well as sufficient, which is that the discriminant of this equation must be an integer. Now this discriminant, as you know, usually you write it in the form b squared minus 4ac. So here this coefficient is the b coefficient. So a squared minus 4b. So that's this quantity here. And for this it is a squared plus 4b. Here you get this. So it's quite easy to see that these 2 must be distinct, non-zero perfect squares. Why non-zero? If it's 0, then the roots will coincide, and we want 4 distinct roots. So, and why should they be this word distinct? If b is equal to 0, then these 2 equations are identical, so you don't want that either. So both these parts are necessary. So now, how are we going to find all possible a and b for which this is true? A squared minus 4b and a squared plus 4b should be distinct non-zero perfect squares. So let one be c squared, let the other be d squared, where b and c and d, and of course a are all in positive integers. This means that c squared, a squared, and d squared form a 3-term arithmetic progression, right? Because the difference between these 2 is 4b, and the difference between these 2 is also 4b. So it's an arithmetic progression. So the task becomes find a way of generating triples of distinct squares in AP. But a happy situation, we already know how to do this. We've already solved that problem earlier, right? And in case you wonder, what about this part? So here we seem to have forgotten the condition that the common difference has to be 4b. In other words, the common difference has to be a multiple of 4. But it's very easy to convince yourself that if you have 3 perfect squares in arithmetic progression, the common difference has to be a multiple of 4. You don't have to insist on that condition. That condition will automatically get satisfied. I think you can work that out for yourself. So I'm just going to use the formula which we already know, which is using this parametric form. You may remember that we got this pair for x and y, and where t should lie between root 2 minus 1 and root 2 plus 1. So these are the triples which we obtained earlier. I'm just reproducing an earlier table. If you choose t equal to 3 upon 2, you get this 49, 160, 7 squared, 13 squared, and 17 squared. You choose t equal to 5 upon 3, you get 7 squared, 17 squared, 23 squared. And that's it. That allows you to generate nice quadratics. So for example, if you take 7 squared, 13 squared, 17 squared, that means A, remember A is the middle one, A is 13 squared, and B is 1/4 of the common difference, which means 1/4 of 13 squared minus 7 squared, which is 30. So you get the quadratics x squared plus 13x plus or minus 30. So both ways you get integer roots, so you get 4 integer roots. And similarly, if you take 7 squared, 17 squared, and 23 squared, you get A is 17 and B is this minus this upon 4, which is 60, and you get x squared plus 17x plus or minus 60. And as you can see, there are lots of nice quadratics, infinitely many of them, enough for all of us. So one problem which I do not consider in this presentation, you can also look at nice cubics. Perhaps you can try to figure out in what ways you can make a cubic nice. Now, where I'm sure you have met cubic curves, you get these nice shapes, cubic curves and cubic functions in your when you start studying calculus. So what might you want about? You may want some condition about the roots of the cubic. It will have 3 roots. You may want to have a condition about the maxima and minima, right? The cubic has one maxima and then another minima. So you have two more such numbers. And then there is the point of inflection, which is in between, halfway between the maxima and the minima. So you get 6 different numbers, and you may want all 6 of them to be integers. That way you will get a really nice cubic. How will you generate such a cubic? Now that leads to a nice problem. I have not considered it here. So I thought it might become an overdose, so I didn't include it in this presentation. So let me conclude by this slide here, that in conclusion, there are more such areas to explore. It is open territory for us. It's infinitely many of them. And as this mathematician who was a contemporary of Euler, in fact, he died in the same year as Euler, 1783. There's this beautiful statement due to him, that algebra is generous. She gives more than is asked of her. I wonder if you see what this means. The beautiful thing about algebraic expressions is sometimes you find, you're working with your pencil or your pen or maybe a computer cursor, and it turns out that what you're writing sort of drives itself, the algebra drives itself, and yields results for you which you never anticipated. So that's why he writes here, algebra is generous. And one such example you may have seen in that problem of the 60-degree angle. From the expression itself, you see that the middle number is always a square, and the sum of the latter two numbers is also a square. Now it's the algebraic formula which tells you that. So I'll stop here. Just these are the references. I need not go on here. So I'll close the presentation now.
Thanks a lot, Dr. Shirali. Yeah. Let us all thank Dr. Shirali for a fascinating talk. You can use your reactions button. And now I'll open the floor to questions. So if you have a question, please raise your hand. The raise hand button is, if you can click on reactions, you'll see the raise hand button. And then I can unmute you so you can ask questions. And if you prefer not to speak, or you would like to just type the question in the chat box, that's possible too, and I can read it out.
Yeah, if anyone wants to ask a question just directly, that's also fine, because we have a few minutes, about 10 minutes now.
Yeah, so I can unmute whoever wants to ask the question.
And if you would like me to say something more about some more of these problems, I can show it on the board here. I don't have it in the presentation.
So I see, yeah, sure, that would be great. But there's a question, maybe, shall I ask the question first? Lakshya, would you like to ask it aloud? I can unmute you. Lakshya, yeah, go ahead, Lakshya.
Sir, you said that we cannot find any 4 terms in AP that are perfect squares. So is there a proof of that, or?
Oh, yes, certainly there is a proof. It's just that the proof is quite difficult. There is a proof, certainly. I can show you a reference to it. In fact, I have it open on my system here. It is rather, no, I'm sorry, I may not have it here. It is rather a difficult proof, that's all. If you try it out yourself, you'll find that you have to, you get so many variables and so many equations that you begin to lose control of the thing. And for many years, it was found that the proofs that people had claimed were defective. Somebody made a claim and then it was found that it has a flaw in it. But there are perfect proofs available. I think you just type this phrase into your search engine, 4 squares in arithmetic progression. You will find it there. But I'm cautioning you, they are quite difficult proofs. They're not, it's a page which spans, proof which spans some 5 or 6 pages. I have not yet come across any short proof, like just fitting into one single page, or just with some simple contradiction. It's not like proving that there is no lattice point equilateral triangle, which was a completely trivial proof. this is not a trivial assertion.
Okay, thank you, sir.
So I won't be able to prove it here. It is too long to give that proof. But I can share it with you later.
I think Indulekha has a question.
Yes, please.
Indulekha?
Yeah, I was just wondering if you could take this idea of lattice triangles with integer sides into 3D, on a 3D lattice. Would it be solvable?
Well, 3D introduces new, you may not be able to solve it using that same idea. First of all, there are counterintuitive things. You have no equilateral triangle in a 2D lattice, but there is a very simple equilateral triangle in a 3D lattice, which is simply the points 1, 0, 0, 0, 1, 0, and 0, 0, 1. You get an equilateral triangle there. So something immediately that is different in 3 dimensions, which doesn't happen in 2 dimensions. So I'm not sure of the answer to your question. I don't know. What techniques, you may not be able to use complex numbers in that. You'll have to just fall back on algebraic methods. I don't think you can use
Fermions?
Yeah, I'm not very sure. Maybe I'll have to think about it. I don't know the answer to that. But it's an interesting question, because in 3D many things happen which are counterintuitive, which don't happen in 2D, as we all know. There are any number of phenomena which can be done in 3D which don't happen in 2D, and now we see something even in this situation here.
Thank you.
Okay.
Other questions? You can raise your hand or type the question. I had a quick question while we were waiting. So you mentioned at some point a geometric proof for things. By geometric, do you mean like starting from Euclid's postulates and giving a constructive argument?
That's right. You look at actual geometric properties of the configuration, similar triangles, similarities of whatever, some equal angles. You look for the geometric properties and the kinds of things that arise from them. And it turns out for that a squared equals b times b plus c, there is a very nice geometric proof for both directions, for the forward implication as well as the reverse implication. And that remark I made out there is important, because it turns out that, and I'm sure this has implications at higher level as well, that the treatment of most of these is so heavily algebraic at the +2 level that we lose our geometric intuition. And because we lose our geometric intuition, that may have consequences in our work later on. We are not able to actually visualize things. Everything we try to reduce to the symbolic form, and then algebra is like a tank. You just go like a bulldozer into the thicket, whereas you may be able to visualize the thing and get a different perspective altogether. For example, Mandelbrot was like that. Mandelbrot, he liked to think completely in geometric terms rather than algebraic terms. And he decried this excessive dependence on algebra, his, fractals and so on.
Yeah.
If you can ask another question.
Yeah, go ahead.
It's more of a comment. Like you were, when speaking about Fermat, you made this comment that he presents these theorems without proof.
Oh yes, that was his hallmark. He used to do so many things. For example, he claimed that there's a beautiful theorem of Fermat's, which is called the two-square theorem, that every prime which is of the form of 4n plus 1, that is one more than a multiple of 4, every such prime number can be written as a sum of two squares. Like, say, 41 is 25 plus 16. 41 is a prime. He made this statement in some letter. Everything he I mean, those days it wasn't, publications, journals, and so on. Everything was in correspondence with other mathematicians. So he made this claim, and he said he has a beautiful proof of it. And he also claimed that the proof uses the idea of infinite descent, which perhaps is his original invention. The idea that you can prove something by contradiction, by successively bringing down the scale of the problem to smaller and smaller numbers. It's a beautiful idea, and he is supposed to have proved it there. Well, I'm not sure whether he used it for this one. Well, but anyway, he made this claim in a letter, but there was no proof to be found in his published work, in his correspondence, anywhere. And it was proved only much later by Euler. The actual proof that we know today comes from much later on. Similarly, he claimed, of course, Fermat's last theorem was a statement that he made casually in some book. And this statement about 4 squares in AP also he made in some letter. So he was in the habit of making such statements. So he must have been an amazingly, person with great feeling for numbers, and he must have been quite a person, because he did this all in his spare time. He was a jurist, and he used to do all his work, mathematical work, probably after he got home from his office.
We see this kind of statement made about Ramanujan also, right? He has also presented results which are amazing, and again in number theory. So
yes, Ramanujan was very, very wide. I mean, he's worked on a very much wider scale, and the statements he made are, of course, of much greater depth. And he used to work in ways which perhaps nobody has ever figured out. Nobody has really understood the basis on which he made some of those most incredible claims. Simply, even 100 years later, people are baffled by it. How could he have made such? And the more discoveries are made, the more people are baffled by these the things that he discovered. It's really beyond understanding. But from what depth he was operating, what kind of an intuition he had, nobody knows. Especially this theory of some of the things which are coming out in today's times, this modular functions and so on.
Yeah. Sorry, Indulekha, did you want to?
I think Sam had raised his hand.
Yeah, exactly. Right.
I would like to ask after that.
Yes, please.
Sam, did you have a question?
No, I was going to ask about Ramanujan, but you've already answered that in some detail.
Oh.
But I was also going to ask about the Kerala mathematicians, who also used to have a tradition of making statements without authorship and without proof often. Do you have any comment about the Kerala school?
It's a bit difficult to say very much, because I think it's still an emerging field. There are people doing research on this even now, on the work of the Kerala mathematicians. It's not strictly true that they didn't prove things. I think the basis of their work is hidden away in other works. It is there. It's not like Ramanujan's work, which it's completely erased. He is reputed to have done everything on a slate and simply wiped out the rough work entirely. But that is not quite true of the Kerala mathematicians. There are some traces in other people's works. But yes, there are some mysteries. For example, there's that famous infinite series for pi upon 4, 1 minus a third plus 1/5 minus 1/7 and so on. And if you stop at any particular point, there is a considerable error introduced. So Madhava actually gives error terms to compensate for that, so that you get very much more accurate values for pi by introducing those error terms. Now, the basis on which he got those error terms is unknown, and they are quite remarkable. It's mysterious how he could have got something which you need much more sophisticated knowledge to prove. it's a bit mysterious.
Yeah. Thank you.
So I think there is P.P. Divakaran has some book he has written recently,
Yeah, that's right.
and he gave some talks also which are online. If you look for Madhava lectures, ICTS, for anybody who's interested. Yeah, I haven't read the book myself, but the talks were interesting, and maybe there's more information about some of the details about this. I had a small comment also related to this fact that, like, of course, maybe Ramanujan is at a different level, but many of the great mathematicians, even contemporary mathematicians, tend to predict things which are not proved. And then there are decades of work of armies of people now. I mean, at Fermat's time, probably there were not so many armies of mathematicians working, who then, for decades work out those programs, and they always turn out to be, at least in their essence, correct, even if there are details that are off, which is the, I guess, truly amazing thing that I guess great mathematicians somehow have a sense for what is right, or
Sure.
what is true.
Yeah, you can sometimes have an intuition of something which is true, but be unable to say why it is true. That is of course so. But then there are any number of unsolved problems still waiting. The millennium problems are still there.
Yeah.
6 of them.
So, are there any other questions? While we're waiting, actually, I have another question, which is a slightly open-ended philosophical question. So, how do, I think this is a subjective question, so maybe different mathematicians would answer it differently, but maybe it would be interesting for the students also to hear your view on this. So, how do you decide, what is beautiful or nice mathematics? Because in the other sciences, so in not mathematics, but physics and chemistry and so on, experiment and the physical world dictates, what is, to a large extent, dictates the direction of the subject. Whereas in mathematics, it's more like art, right? We can create within the rules of the game, we can create whatever we want. So what to you is, perhaps it's not easy to put this in words or say it in words, but what to you is the sense of what makes mathematics, a particular kind of mathematics, beautiful or, good mathematics?
It's a very nice question, and not easy to, it's a very rich question. So one can actually talk about it, discuss it. I think perhaps simplicity of form. Form is certainly very important, the form of a result. And another is the connections that you see in something. Suppose a result, you discover a result, and it turns out to be, you find that it's exactly connected to some other result in some totally unconnected, apparently unconnected area. So that's one thing which is tremendously pleasing to anybody in the field of mathematics. And I think simplicity of form also is very appealing. When you have something which reduces to a very simple, compact statement, which can be just written in one, for example, saying that every prime of the form 4n plus 1 can be written as the sum of 2 squares. It's a remarkably simple statement and not easy to prove. You would have to be quite an expert to be able to prove that on your own. That's something with great beauty, something which anyone can appreciate with minimal work. So I think all these are factors which go into it. You can't give it's a subjective thing, as you said.
Definitely in what you talked about, this aspect of many things coming together was also present, right? Like algebra and geometry and number theory all tying together into, I guess, the beginning of algebraic geometry.
Quite right.
So
any other, are we out of time? There's one question. Can I take?
Oh yeah, maybe one question can be admitted.
Okay, let me unmute. Lakshya, could you unmute yourself and ask the question?
Yes, sir. I had read somewhere that Gödel proved that mathematics is incomplete, that there are bound to be some questions which are true but cannot be proven or disproven. So maybe we can come across some of these things and spend many hours or even years to prove it. So then, sir, how can we decide that it is unprovable?
Yeah, this is a very difficult question to really discuss. But in the 1930s, Kurt Gödel, he discovered this most completely counterintuitive result, that it is possible for a statement to be true within some axiom system, and yet the rules of that axiom system don't allow you a path from the axioms to that result. You can't find a way of getting from here to there, even if the statement is apparently true. So I mean, that's what he discovered. It's impossible to really. I mean, it's a very counterintuitive statement. So, of course, the immediate question arises: how will you ever know whether a statement is of this kind or not? And the answer to that is to play around with the axiom systems and show that it is possible to have an axiom system in which the result is not true by tweaking some axioms. So the most well-known example perhaps is the parallel postulate of geometry. They attempted to prove it using the earlier axioms. And try as they did, they could not. And finally, they accepted it as an axiom. And then it turned out that if you contradicted that statement, you could get a valid system of mathematics, which is the non-Euclidean geometry. So in a way, that's what you have. If you have a statement whose contradiction is not inconsistent with the axioms, both ways it is not inconsistent, that means you have a statement which cannot be logically proved from there. So there are statements which have been found of this kind. The most well-known is probably the parallel postulate, but in number theory, in set theory, they have found such examples and so on. So, but I don't think I will be able to say more. It's a very deep topic. And I might end up saying things which are not quite accurate also. So, but this is basically that's what the subject is all about. Decidability, undecidability.
Thanks a lot. I think there may be many other questions as well, but we are out of time. So let's thank Dr. Shirali again for a fascinating lecture.
Thank you. Thank you very much.
So thank you, Professor Shirali, from the organizer's side also.
Yeah, sorry. I just wanted to say that, since this is the last talk of this section of the Resonance lecture series, let us thank the Indian Academy of Sciences, the ISER Trivandrum and ISER Mohali, as well as everyone who helped organize this and put this together, all the staff and the organizers for putting this together. And there is also tomorrow the section of this lecture series for undergraduates will begin, I think at 9:45. Indulekha, would you like to say a few words about, you wanted to say something?
Yeah, from the organizer's side, we wanted to thank all the chairs, that includes you. So thank you for today's chairs, Nisha Kannan and Pranav Pandit, and all the speakers, Professor Karandikar, Kavita Ishwaran, Professor Vishwanathan, and Dr. Shirali. And thank you all the chairs. And thanks to the audience. Thank you all students. I hope you enjoyed all this scientific feast that has been put together by all of us, and the speakers have been amazing. Like just now what you heard, this peep into mysteries and beauties of numbers. So thank you everyone, and we come to the end of this 2-day program for high school students, which is being conducted as part of the Resonance lecture series, celebrating 25 years of Resonance. Thank you everybody once again.
Thank you very much and goodbye.
Bye.
Thank you. Bye-bye.